Maulana Azad National Urdu University, Hyderabad, India. Welcome to our course and welcome to the first lecture of this course, which is on astronomical data. As you know, this course is basically centered around astronomical data, where we are going to basically show to you how we use archival astronomical data to do various projects and study astronomy in much depth. So astronomical data is the center of what we're talking about. Now, what you see in this image over here, it's an image of a globe where you actually have constellations marked over here. And these position of the constellations, they actually point down to a date of about 125 BC, which actually matches to the catalogue made by the Greek astronomer Hipparchus. And Hipparchus was amongst the earliest to catalogue data about stars, their positions, their brightness, in a very systematic manner. And that's exactly what we call astronomical data. If you observe the sky and catalog or get your data, record it in some form, which can be organized and used. What is the present terms and types of data that we have today? Most of the data that we have today is digital data. Even data which was got earlier as photographic plates has been digitized. We'll talk about it in a bit. And often the data could be either in-depth study of individual objects in the sense of what we call targeted observations, or they could be survey data of a larger or probably even complete sky. And these data sets have a very large amount of data that they are handling. So for example, the IISER Vista survey, it handles about 150 terabytes of data per year. The LSST telescope, or the Vera Rubin telescope, it would do about 500 terabytes per month. Okay. You also have data which is from simulations. For example, the simulations, we talk about that later, TNG 300, 300. This is giving you more than a few petabytes of data. This is the 2018 release. And therefore, since you have such large data sets, these data sets need to be housed in data centers, which basically house all the data from these data sets, since they are so very large. And it's not just one data center. You could have many mirrored data centers, which actually mirror also the same data so that users can access it from various sources. The data can be also handled using programming, for example, with Jupyter notebooks. So one can actually write code to access the data and actually manipulate the data and get it in a certain format as per your requirement using Jupyter notebooks. We won't be talking about Jupyter notebooks today, but we have some separate sessions specifically for Python, where we'll be starting right from the basics and taking you up to a level at which we can actually access astronomical data with Jupyter notebooks. Now, what is the kind of data which we're talking about? The data could be just images. From images, you can create catalogs. That is, you actually look for objects in your images and make catalogs out of them. You could actually have individual spectra of objects. You could have polarization data. You could also have what is called time series data. Time series data is, for example, you have a variable source and you measure the brightness of the variable source with a certain time cadence or whatever time step, and that could give you what is called a time series data. Now, what is the, for example, let's come to the first kind, which is the most basic kind, which is an image. We're talking now about digital images. So if we talk about digital images, what are they? It's basically a two-dimensional array across X and Y. And you have some pixel value, okay? And the pixel value is actually giving you the brightness at this certain point, okay? Such an image would essentially be a black and white image where you actually just have counts at different points on your XY grid. Now you can use such an image to actually create what are called RGB images or color images. In astronomy, we often use what are called artificial colors also. You may give colors to an object depending on their wavelength or their energy. So for example, you may put your more high energy objects as bluer, your lower energy objects as redder, and you may hence artificially create an image of the object which you're actually looking at. Now, what are the kind of objects you actually look at? You could either be looking at point sources or extended sources. Point sources, for example, galaxies, and an extended source for, a star, for example, or extended sources, for example, a galaxy. Now, what is the basic paradigm shift which came into imaging in astronomy? Actually came with the event of the CCDs. The CCDs are what we call charge coupled devices. And they were basically invented in 1974. And you have a picture here of Boyle and Smith. These are the inventors of the charge coupled device at Bell Labs. And this is what has got a major paradigm shift in the understanding of astronomy imaging since those times. Now, what is the basic advantage of CCDs? CCDs have a basic advantage, the most important being what is called the sensitivity, or what we call the quantum efficiency. So you can look at the quantum efficiency. It's basically telling you how many photons which fall on the CCD actually get detected by the CCD, right? How many of them get detected? So for example, if you take your eye, right, and you have say 100 photons, you may actually detect just one, right? But for example, if you have a photomultiplier tube, you're improving it. And as you go on to CCDs, you're actually achieving about 80% or more than that. That is, your 80% of the 100 of the photons which actually fall on it are actually detected by your CCD. And that's what's called the sensitivity or the quantum efficiency. And that's very crucial, especially in astronomy, because the sources you are looking at could be faint sources. And therefore, every photon you get from that source is precious, right? You would like to detect every photon that comes. The other thing is your dynamic range, that is the brightness of objects that you can actually see how faint and how bright. This can also be changed by basically because with your CCDs, you can change your exposure times, how long you're going to observe your object. Based on that, for example, if you have a very bright object, you do not observe it for too long, otherwise your CCD will get saturated. But for the fainter objects, you need to have a longer exposure, and hence accordingly adjusting it, you can adjust the range of the objects that you actually look at. The other very important part about CCDs is its linearity. By linearity, what you basically mean is, you look at this plot over here, is that supposing you have an input versus an output, as your input increases, your output increases, and this goes linearly. So for example, if I were to use my CCD to observe say for 1 hour and get say 5,000 photons, if I observe for 2 hours and I get 10,000, this is linearly increasing in terms of the output signal, and therefore I can integrate for a long time. So for example, if I want to observe an object for 10 hours, I can do that as long as I keep on adding on. You can see over here that after a certain stage, you can have something called non-linearity. That is, after some time, you could have your pixels saturating. And so then if you even increase your exposure time or the input, even if you increase the input, the output does not increase proportionately, right? And therefore, in this case, but for these both 2 points, it would be very difficult for the observer to say how has the number of output photons giving you the correct amount of input photons, because for the same amount of output photons, you have two different input photons, right? So what you basically want to do is, in the linear regime of the CCD, you want to detect so that you can use the addition of frames or the addition of photons to actually get your signal to much better efficiency. And therefore, you can actually do this with CCDs, right? For example, with our eyes, we cannot do that. We just have a certain period in which we detect it and we cannot add on, right? In this case, we can actually add on, which was there even with photography. Only disadvantage being saturation happened much earlier, and therefore you would already reach the non-linear regime once the photographic plate starts getting saturated, right? While in this case, you have a much larger linear regime, and as long as you work within the linear regime of the CCD, you are going to get a good data set, right? And so this is the way you're actually getting digitized data, digital data, because you're digitally detecting it. Digitized data means that, for example, if you had photographic plates, you can use that to actually digitize it. But you know that your photographic plate itself is a nonlinear detector, and hence by digitizing it, you are, you do have some errors which are coming in because you're not necessarily in the linear regime of your detector. Now, how do we actually get colors in our images? So what Eastman Colors, Kodak, the company Kodak did to actually get colored photographs was to use something called a Bayer filter. So what a Bayer filter did is that basically you have a square grid of photo sensors, right? And these photo sensors are sensitive in different wavelength regimes, right? So for example, the green one is more sensitive for green, the red for red, blue for blue. So what you actually did is you had a grid of these green and blue sensors on it. And this is what is basically used even today in digital cameras, in camcorders, in video shooting, etc., where you actually use this to actually get your RGB image, because different parts of the pixel are activated by by photons which activate the blue, red, or the green region. And using this, you actually get a colored image. So this is how we get the basic color images which we use for all our digital photography, cameras, videos, etc. Even the video that you're looking at just now. But in astronomy, we do not do this. In astronomy, we do a slightly different approach. You know that the signal, the input signal is not going to change much with time. And therefore what we do is we actually use filters in succession. So when you're actually getting your image, which is your basic black and white brightness image, you actually put a filter in front of it and get some kind of readings which you have for the filter in the beginning, say with the blue filter. You then do it with the wheat filter, and then you do it with the third filter, we say the R filter. And using that, you will actually get 3 different images of the object, right? And then we use these 3 different images to overlay them. We will do that in future to actually create what are called RGB images. So in that, what you do is you exactly overlay objects and you place them. So for example, on the left, you can see this is an image of Westerland 2, which is a star cluster. And you can actually see this has been observed by a 2-meter telescope. And what they did is they overlaid different filtered images. While over here, what you see on the right is this is a Hubble image. In a Hubble image, they basically also overlay, but they also use artificial colors. So you can see here, these are regions which are dusty regions, but to enhance the dustiness, you actually put artificial colors to actually show these different parts. And using this, you would know which is the part which has the hotter gas or the cooler gas, etc., depending on how you characterize the colors of your image, right? So here we have an example of artificial colors being used to create an image. Now in astronomy, we actually use a certain thing for images. We use a certain format, which is called the FITS format. You may be familiar with formats like the JPEG or the, the other formats which we use for a GIF image, right? But those kind of images actually lose out important data which is required in astronomy, right? And therefore in astronomy, we use this FITS, which is the Flexible Image Transport System data, which is actually a system which is used to store data. It puts it as a 2D image. It can also put it in the form of a table. It also has extra information which is called a header file. A header file has different information about the image itself. For example, it tells you which telescope observed it, on what date, and for how long was the exposure, with what filter times. So it's kind of packaged with the image. So with the image, you also have packaged along it information about the image. Like I said, the filter, the exposure time, the telescope, etc. It's all put it along with it. And it's basically used to actually store this data. The data can be also, you could even have spectra in this format, you can have data cubes, and you can have various kinds of data which are put into this FITS format. Another important thing about astronomical data is the brightness. When you actually look at the brightness of objects, when you display, right? When you display an image, what you see on the left, this first image over here, is you can see an image where the scaling, the brightness levels of a monitor would be 2 power 16, which is about this, or 65,000 counts would give you the brightness. If you were to actually just scale an image based on the counts, you would get an image something like this, which would get displayed like this, which does not convey so much. So therefore, in astronomy, we actually play around with image displays. We try to see how can we display our image in a much more effective and a much more, beautiful manner, which actually shows out. So for example, here I've shown an image which actually rescales the original image such that now you're scaling it such that you're only taking counts from 4,572 to 6,002. So this image basically has counts up to about 6,002. So you don't want to, you rescale your image. So you can rescale it linearly over here. And then there are other techniques of scaling it, which is square scaling, which we have over here. So I'm going to show you some display software, which is actually used to display astronomical images. And what we basically do is we rescale the brightness of images to enhance the properties of the image, right? Otherwise, if we were to just take it on counts, we would get things like this. But we actually use some techniques to actually enhance the display of images. Now here you have an image, a very nice image of NGC 281. And you can see how nice, colorful this image looks. But it's not that this image actually has purple stars, right? These are not purple stars or blue stars, whatever you think. And a lot of this image is basically made up of artificial colors. But what we do is we have these artificial colored images and we overlay it with other images. So for example, this image is basically an overlay of two images. One is an image which we have from the telescope called Spitzer, which actually observes in the infrared. So if you look at this part, this whole part is from the Spitzer image, which you can see this thing over here, these pillars and this jutting out part over here, which you can see over here, which is from the Spitzer image. What we do is we basically rescale it to actually give it certain, enhancements, or depending upon the kind of brightness we are getting. So this is in a certain filter, in a 3.6 micrometer filter of Spitzer. This basically shows you this image. Now, the same image was also observed with Chandra, which is an X-ray telescope. And what you see, the big square over here is the footmark of the Chandra exposure. So if you can actually see over here, when Chandra observed it, it basically is an X-ray telescope. So it's looking at very hot stars. And therefore, the artificial color which was applied to the Chandra image was blue or violet, because it's basically showing you very hot regions, very high energy photons. And this is NGC 281 by Chandra. Here we had it by Spitzer, and here you can see it by this. So what has to be done is very carefully you overlay two images so that they lie exactly one on each other with the right scaling, with the right angles, etc., so that they actually sit. And what does this tell you? This basically shows you that in this region, which are the sources, which are X-ray sources, which are the infrared sources, and where exactly does this gas and dust lie around over here. So it basically helps you to see the interplay between the gas and the dust and the hot stars, right? So by using this kind of overlaying of different images in different wavelengths, in different energies, we can actually use this to unravel the physics of this region, to actually see what's happening to these stars, which are the ones which are emitting and which wavelengths, and what is contributing to what in this image, right? The other kind of data you could have, like I mentioned earlier, is what is called spectral data. What is spectral data? Spectral data basically means is that you are actually checking what is the energy distribution by a certain source of light in different wavelengths. So for example, if this is the range of wavelengths, you are seeing which one is brighter, which one is fainter. So you can see these are absorption lines, and therefore here these are black lines, and you are seeing which wavelength you have these black lines at. So this is telling you how does the intensity vary with the wavelength, where are these dips coming. So it tells you that this source of light, whichever you had, it's giving you some absorption at some particular wavelengths. Now, once you measure the wavelengths accurately, you can actually identify which is the element which is going to give you this kind of absorption at those wavelengths, which can contribute to creating a spectra of this kind, right? And therefore, that's how your spectra are created, by basically getting this. So what is a spectrum? It's basically a one-dimensional data, because it's basically telling you how does the source vary in its brightness at different wavelengths, right? Now, what happens is in today's telescopes, we also have what is called, you have what is called integral field spectroscopy. That is, for example, you can actually get the field, the spectrum for every pixel on the object, right? So what you're actually going to get is each pixel actually has a spectrum received from the, has the spectrum. So for example, if this is a galaxy, you're looking at a galaxy nucleus, you can actually look at it like this, in the sense, if I take this pixel, if I look into it in depth in terms of the cube, it's going to tell me how much is it emitting in blue light, in green light, in red light. So I'm going to get a complete, in this way, I'm going to get a distribution in terms of wavelengths. If I cut it as a slice, it's going to tell me how does this nucleus behave in a particular wavelength. For example, if I have the Balmer line of hydrogen, I can take a slice in the Balmer line and see in the Balmer line what's emitting. So I can see in the galactic nucleus what is it which is giving me the hydrogen spectrum, right? So I can take slices which would be like this, which would give me the distribution in XY for a particular wavelength. Or I can take a pencil, I can poke a pencil into this, which will actually tell me for this particular pixel, what is the distribution of light in different wavelengths for that given pixel, okay? And now this data is generally stacked up into what are called data cubes, Because you can understand that if you were to actually keep it in terms of separate files, it would be very confusing, very difficult to handle. And hence this is kept in the form of a fixed file, which is a data cube. So the fixed file has a header file which actually tells you what is the object you're observing with, using which telescope, what exposure times, what filters, etc. And then you have a data cube, which is actually slices of these, which are all stacked up together. So then, for example, if you want to look at it in a particular wavelength, you can look for the slice which carries the red data or the blue data or whatever wavelength you are looking at. So data is also kept in the form of these data cubes, right? So it's a three-dimensional data set. It is X, Y, and the pixel and the spectrum per pixel. Now, why do we need things like this? For example, if you're looking like at a galaxy, like this galaxy over here, supposing you have the spectrum for different points in this galaxy, you can look at over here. I can use the spectrum to actually get velocities, right? So for example, I get velocities for different points along this galaxy, at the center, at the middle, at the edges, etc. What can I use that for? I can use that here, for example, in this case, to actually get the rotation of a galaxy. So what you see over here is I have a galaxy, and you can see that here you have the lines which are actually getting redshifted because they're going away from us. Spectral lines, the ones coming towards us are getting blue shifted. You can see that the edges are coming to us at a faster velocity than the central part. Similarly, this edge is also going away from us at a faster velocity than this, right? So this is the way you can actually measure rotations of galaxies if you have an integral field spectra of those galaxies. The other kind of data you can have is what is called catalog data. So for example, catalog data is basically tables. So you have tables. For example, here I have a table for clusters. So there's a cluster name. These are the coordinates, the right ascension, the declination, galactic longitude, galactic latitude, the radius for the 50 stars in it, number of stars, proper motions, etc. So these are like, these are like spreadsheets. They are catalogs. But in astronomy, we handle that far better using something called TopCat. And TopCat is the thing which is used to handle tabular data. We're going to have a separate session on TopCat from the writer of TopCat, the person who actually did TopCat, is called Mark Taylor, and he'll be telling you about that on the 22nd of August. So that's when we've handled catalog data better, the TopCat, this thing. You could also have time series data. For example, I have a source, and you can see that every day, that if this is the days, every day the brightness is changing, and therefore this could be in a tabulated form, which basically tells you how is the brightness changing on various days, right? So you may put it in the form of the y of t, which is over here. So that's your time series data. We will also be talking about various tools which are used for visualization of this data. For example, the simplest tool which I will show you all soon will be the image visualization tool, which is called DS9. There's also a tool for catalogs, like I told you, it's called TopCat. And there are programming tools. For example, essentially what is used in today's times are Python. And we're going to have special sessions on Python, which will basically show you the modules, the libraries, etc., and how to use Python for astronomy data. And all these have to not be used as black boxes, right? They are useful tools, but you need to understand your tool very well so that you can effectively use your tool to get some amount of data or understanding of the data that you have. Along with the data, you also have what is called metadata. There's always, like I said, in the fixed file, there's descriptive information about the data, which gives you information like what are the telescopes, the exposure times, various things about the data, and that is what is called metadata. So metadata is data which kind of supplements data, which gives you data about the data. It tells you how was the data got and what is special about the data, right? Now, what is an astronomy archive? We already had a look as to what is the kind of astronomy data you could have. You could have images, spectra, catalogs, time series, polarization data. But what is an astronomy archive? When you actually look at the sky and you put the data in the form of an organized, systematic form, that's what we'd call an astronomy archive. And like I mentioned today, that there are already archives which are many terabytes and petabytes inside. There's a very large amount of data which is already available to our benefit, which is there, which is very good quality data, because a lot of this data is from space telescopes. Some of them are from very large ground-based telescopes. And these are very good quality data. It's not that it's leftover data from which there's nothing. It's instead very useful data because it's very high quality data, and there's still much more potential in that data of the kind of science you can get from this data. Now, like I mentioned earlier, the earliest archives we have is of Hipparchus, where Hipparchus actually tried to tabulate, but Hipparchus, the catalog was a very small catalog, just 850 stars, which were kept in magnitude scales. We'll talk about magnitude scales tomorrow. That is a scale in which we describe the brightness of objects from magnitudes 1 to 6. And he actually set up that scale. What you see on the left here, you see Tycho Brahe. He was a very talented observer, and he actually very well tabulated the positions of naked eye planets as a function of time. And one of the first examples of use of archival data was the data used by Tycho Brahe, which was used by Kepler. Now, Kepler actually used Tycho Brahe's data to actually study planetary motion. You know, these were the times when people were still arguing about whether we had a geocentric system or a heliocentric system. And the basis of that would have been the observations of planets. So if you actually observe planets, see how they are moving, you can actually decipher what kind of orbits they have to understand the structure of the solar system. And that's exactly what Kepler did, that he actually used his data, Tycho Brahe's data, to actually decipher the movement of planets in the solar system, on the basis of which he set up what was called the 3 laws of planetary motion, which are Kepler's laws of planetary motion, but they're all based on the data which was got from Tycho Brahe. Because as we always know in the scientific method, what we actually use is you have to have observations which comply with the theory. If they do not comply with the theory needs to be changed so that it adjusts with the observations. And once you get contradictory observations, the theory has to go hand in hand with the observations, right? So later on, people continued the system of making star catalogs. So in 1603, Bayer made a catalog labeling every star in a constellation by its brightness. So what he did is he identified constellations. The brightest star, he called it alpha. The next one, he called it beta. Then he called it gamma. So in that way, for every constellation, he named alpha, beta, gamma, etc. and named every star in the constellation. In 1771, Charles Messier actually made a catalog of nebulous objects. And basically what he was doing is he was basically looking at cometary kind of objects. So these were fuzzy objects. Some of them actually turned out to be fuzzy objects in the sense of nebulae, etc. While some of them, with better telescopes, if you looked at them, you could actually resolve them to be galaxies or star clusters, globular clusters, etc. But that gave Messier catalog, which is about 100 objects. The Messier catalog is still used by people to actually look for deep sky objects. And then you had the NGC catalog, the Dreyer catalog, and all these are examples of organized data where you actually observe the sky, you organize what you observe in a category, you know, in a systematic way, which can be actually used. Now we're going to jump in time, and one of the earliest sky surveys where people actually tried to study the whole sky was done by Palomar. In Mount Palomar, you have a telescope, and what they basically did is that they actually used these photographic plates, which you can see over here, which have a size of about 14 inches square, right? And using 2000 photographic plates, they actually covered the entire sky, okay? So each plate would cover 36 square degrees of sky, and using that, they actually got plates which would cover the whole sky, observations of the whole sky. This obviously covered the northern sky. Similarly, sky surveys were even done for the southern sky. And these were in the form of photographic plates. So what you can see over here, you have this instrument where you're actually looking at the plates, okay? And later on in the 1990s, what people did is they actually digitized it. That is, you actually looked at the plates and put them in the form of a digital form. So now if you actually Google it and you actually Google DPOS, you'll actually get the digitized Palomar survey, which will actually give you the digital form of those same photographic plates. So that's how it actually started, where with Palomar, they started doing this digitization. And then you're already 50s, 60s, 90s. And then when you see in the last 30 years, 40 years, there has been a real difference in the kind of technology which we are dealing with. Now we are actually accessing digital data, right? So I already spoke to you about CCDs, charge coupled devices, which are shown over here. A small CCD chip over here is shown to you over here. Like I said, these have an excellent quantum efficiency as well as a linear response. And therefore, what you basically had is, in the DPOS survey, you actually had photographic plates which were then further digitized. But here you are getting first-hand digital data using CCDs. And that's how you actually started getting CCD images. You also had a big change in the technology. So you can see the technology in terms of computing technology. It improved much more. You can actually see how computing power has increased with time, from electromechanical to vacuum tubes, transistors, integrated circuits. We've actually moved on to very high speeds of computation. And even the phone you hold in your hand has such a good computing power that it can actually compute a very large number of things. And using this, we actually have what are called citizen science projects. That means even citizens can actually access data. Oh yeah, I need to mention the internet. The internet is one of the greatest boons that we have of modern times. And that's how people can access all this data, which is available, talk to each other, and do things. And that's exactly what enables us to do this course also, which we have over here. And that's thanks to the internet. And the internet has actually brought in that kind of a democracy in science, where now data is available to everybody. Wherever you are sitting, you have access to libraries, you have access to information, you have access to data, you have access to anything that you would want, right? As long as you know what you're looking for and you know how to apply the knowledge that you have. Now, this essential change happened in CCDs, basically in optical and infrared. And then CCDs were also applied on to using into, for example, X-ray telescopes. So you had a sudden boom where people could actually then observe in other wavelengths also, which include the radio wavelengths, the X-ray wavelengths. So you have all these things happening together in the last 30, 40 years, that people are observing the sky in an organized way, in a digital format, ranging from X-ray to radio, which includes optical, near-infrared, etc., various wavelengths, as well as with very high computing power, as well as good internet speeds. And so you see, technology goes hand in hand with this amount of data that has been collected with astronomy telescopes. You also have very high technology. You have computing power, which is shown over here. You have the internet. You have, you can use the internet from your laptop, your phone, your tablets, etc., desktops. And as well as a very large amount of storage capacity. We have very large storage capacities to store data. And that's how now there's such a big boom in astronomy archives. And this is really very nice, because this is the true spirit of science, because data is available to everyone. Except if, for example, if you observe with a certain telescope, if you have written a proposal to observe with it, you may have a certain proprietary period. That is a period when the data is purely yours. But after a certain period, which is often something like 18 months, the data gets available to everybody, right? Instrument groups, they have more access to data in the beginning while they are still trying to, calibrate their instruments. And hence, because of that, we have various citizen science projects. That is, even citizens, non-scientists also can do a certain amount of scientific data. So you can even Google and look for the SETI project, which is the search for extraterrestrial life, where people can actually log in and offer their computing power to actually help analyze SETI data. There's also the Galaxy Zoo, which is a very large citizen science project where a lot of citizens are actually sitting and classifying galaxies and their morphology, because basically the data size is so large that astronomers cannot be doing it. So anyone who offers their time and their effort can actually sit and analyze the data and categorize galaxies as per their morphological types. And so I will pause over here, and we'll talk about the data archives in the next section. Thank you. Hello, I'm Dr. Priya Hassan, and welcome to our second lecture on astronomy data. Now, in the previous lecture, we spoke about astronomy archives, that we basically spoke about what is astronomy data, what is the kind of data you could have. You could have images, spectra, time series, catalogs, etc. And these astronomy archives are basically systematic observations of the sky, which have been kept and preserved since a long period of time. Now, astronomy archives are in the true spirit of science, basically because you have a whole lot of data available to everyone. And as this general principle which is done, if you have a telescope, what is generally done is that initially the instrument groups have access to the telescope because they are trying to calibrate their instruments, check the, the behavior of their instruments. And after a certain time, even if people apply for projects and they say they want to observe using a certain telescope, for a certain period, for often 18 months, it's called the proprietary period, the observer, the proposer who proposed to observe, he actually has the data. And after an 18-month period, the data becomes available to the community. And basically the community is free to use the data for whatever they would like to do after the 18-month or the proprietary period. Now, the advantage in this being is that if you have very good high quality data and people have actually used it for a certain purpose, with a certain problem in mind, the same data can be used by many more people in another way. And this is basically to encourage people to get out the maximum they can get from this data. Now, the archival data is often of very high quality. So typically all space telescope data, whether it's Hubble or Chandra or Kepler, TESS, whatever you'd like, all the space telescope data is archived so that you can have it. So it's very good quality data. And also a lot of ground-based telescopes also have their archives. So all this data is very good quality data, which can be used for, a very good effective purpose. And that's essentially what we are even going to study about in this course, where we are basically going to look about what is the different data that is available and how can we actually use this data to our advantage to basically study different problems in astronomy and astrophysics. Now, since there's so much of availability of data, people also encouraged what are called citizen science projects. Citizen science projects are projects in which you encourage non-astronomers or citizens to actually do astronomy projects. So, for example, there was a SETI project, which is Search for Extraterrestrial Lives, where people could extraterrestrial intelligence, where people could actually offer their computing power to analyze the SETI data. Similarly, the Galaxy Zoo experiment was an experiment where actually a large amount of data was available about galaxies, and what was required is that you wanted human intervention in actually classifying these galaxies based on their morphological type. Essentially whether they are spiral or elliptical or whatever kind of galaxies. And it's obviously not possible for a group of astronomers to do that. And hence what they did is that they did a certain initial training period for citizens, after which citizens could themselves opt and classify galaxy data in the Galaxy Zoo experiment. So basically this was to categorize different kinds of galaxies, put them into different morphological bins and study their properties. And this actually led to publications, official publications of the Galaxy Zoo data, because you actually got such a large number of volunteers or people to offer and help in this archival data. So I would say that archival data is the way to go ahead in today's times. Now, if you actually see, we can you can actually see that there are various data archives which are available. What are data archives? Data archives are basically locations where you're actually housing or keeping this data, right? So one of the most effective or the useful data archive is Vizier. I'm going to show you a demo of how to actually use Vizier. So Vizier is actually a place from where you can access various articles, as well as you can access all as published astronomical data and astronomical catalogs which have been given out from the Vizier database. And the other one which I've mentioned here is SIMBAD. SIMBAD is an astronomical database which gives you basic data, cross identifications, bibliography. For example, you have a certain object, you want to know who else published articles about it. There is the NET, the NASA IPAC extragalactic database for multivariate fusion of data for extragalactic objects. There is a Stone Digital Sky Survey which already has its data release 15, where you have a systematic map of a quarter of the sky, producing new catalogs for the deep sky. There was the 2-mass survey, which was actually a map of the entire sky in the near infrared. Then the European Southern Observatory, they have their data archives where all their telescopes data is available on the website, and you can actually access the data and use it effectively. There is the MUST, or the Multi-Mission Archive at Space Telescope Science Institute. This is basically, it houses not just the Hubble data, but also houses data in the ultraviolet, the GALEX data, near infrared, and various other data sets are also housed in the MUST data set. There is the 2-degree field survey also, which has a spectroscopic survey for a lot of galaxies. There's also the IPAC or the IISER, which is NASA's infrared and sub-millimeter astronomy database. And we're going to have a talk on the 29th of August by Louisa Ribul, who works at the IPAC IISER. And she's basically going to tell us much more about the IPAC IISER database. There is the Hubble Legacy Archive, which optimizes science from HST, providing enhanced Hubble products, browsing capabilities. So there are various data places. So the idea is basically to know where are these different data centers where one can actually access data. So I would encourage you all to individually look at these various websites which I'm mentioning over here and actually see how to use them. They are all pretty, user friendly, and it's just a little bit of practice. If you have on some of the data sites, you'll actually know how to use it. So for example, the multi-mission archive center which you have over here, you have this is the Hubble Space Telescope. This is the upcoming James Webb Space Telescope. That's the TESS. This was the sequel to Kepler, and K2, which is actually the Kepler mission, but in the second phase, the K2 mission. So you can access all these data sets from this website. There's also the Hubble Legacy Data Archive, where you can actually access from here. Again, you can have a look at the website and you can actually see how to access it. You see, you can give the position of objects, you give the radius in which you are searching around the object, and you can actually choose the instruments you are looking at, which ones you want to form, and etc. And in that way, you can actually look at this archive. The other archive which I'd like to show you would be the one that we have over here, which is coming up. Which is over here. So like I mentioned, the MUST archive has Hubble, Kepler, GALEX, FUSE, etc. And you have the Hubble Source Telescope catalog, and you have various catalogs also available at this website. The latest website, which is the most useful one, which is the IISER satellite, which is Gaia. It basically offers for the stars in our galaxy, a billion stars in our galaxy. It basically gives you astrometry, very perfect positions. It gives us parallax, which actually gives us distances. We'll talk about parallax tomorrow, so you know what's parallax. Radial velocities, proper motions in RA, proper motions in DEC, and various other parameters. And basically, this is a satellite which has 2 mirrors with which it is actually very accurately measuring positions and motions of a billion stars in our galaxy, right? And this can be directly accessed from the Vizier site, from the Gaia site, which is IISER Gaia, as well as we will have separate sessions where we will talk about specifically Gaia and how to actually access the Gaia data. India has a GMRT, which is the Giant Meter Radio Telescope, which is in Pune. And you can actually see that the GMRT also has an online archive system. So you can actually look for things based on the proposal code. Supposing you knew what was the proposal, people observed it and the time. So for example, if you pick up a paper in radio astronomy, which has observations from GMRT, where you have the proposal code and you would like to work out the paper, try to do it for yourself, you can actually put in the proposal code, get the data, and try to analyze the data the way it is described in the paper. And then it could also be possible that while you are analyzing it, you realize that it could be done in a different way, or in a much more intuitive way, which can give you a certain result. And you can kind of play around with the archive in that way. So this is the GMRT archive. Chandra is the X-ray telescope, which is still operational, which has its own website. And from the website, you can actually access the archive. You can see it over here. This is the archive. There are various tools which can help you to actually search and retrieve data. So for example, JSON, etc. And there are very, very good helplines on these websites, which actually tell you how to handle the data and what exactly can you do with the data, and what are the kind of results you can get. SDSS, I already mentioned to you earlier. This is called the Sloan Digital Sky Survey, which actually has the most detailed 3-dimensional maps of the universe ever made. And this is already into this DR15. And you can see over here that if you go to the Sloan website, you can actually look at the data, surveys, instrument, and collaboration, education. and you can actually see the publications that people have done using this thing. So spend some time looking at the SDSS site. And the other thing I wanted to now end with is a short demo on Vizier, which I will show you. But before that, I'll talk about the data archives itself, that we are going to have individual sessions about each of those data archives, which I mentioned to you, whether it's Gaia, whether it's the Musk data survey, whether it's Chandra. I'm going to actually show you demos on all of them, for many of them, we are trying to actually get people who are over there, working over there with those data archives to actually talk to you and tell you things about them, right? So after that, I'll talk to you about the Vizier catalog, which is the literature survey catalog or data survey. I'll do that next, the next video. Thank you.